Mm-hmm.
Just because I wanted Cindy a book. I don't know what that, I actually gotta be able to get a picture of this.
I can take pictures with my phone too.
Hmm?
I can take pictures of my phone. I'll just match them up later.
Because this is a very, it's called the 164 HT burner.
Now, is it burning up or down?
No, straight.
Burning straight. Oh, I see. Okay.
Yeah. What you have is a rocket nozzle set on its side, and the material was put in behind it
Okay.
to simulate a reentry.
Okay. Right.
That's the color photograph. And
I got it.
yeah, it'd be right.
Let me know if you want me to hold something.
Now this is the black and white one.
Okay.
That's an article on
I see.
what we did and why we did it.
Okay.
So, see, because Apollo, my career in Apollo did not start on Apollo.
Right.
You know,
Where
my
did-
career started in 1956 when I got drafted into the Army.
Mm-hmm.
I went to work for NASA.
Mm-hmm.
Well, I was 2 years in as a GI.
Okay.
That's when I did all this work. And that's
So-
when the first object was recovered from space.
So when you were working as a GI, what was your what kind of things were you trying to accomplish?
The
Just getting the stuff, getting objects back from space.
When I went into the Army, I was sent down to Huntsville, Alabama, because in order to get through school, I worked in commercial steel traders.
Mm-hmm.
As a tool hardener, I had temperature of 2,000 degrees that I consistently worked with.
Right.
When I got drafted, because they had a thing called Scientists and Professional Program,
Mm-hmm.
they sent me, well, after basic training, they sent me to Huntsville, Alabama, with the Army Ballistic Missile Agency as a GI.
Okay.
I got in, and the day I got in, they said, you're going to be assigned to the research and development group. We want to develop materials that can go into space and come back.
Okay.
No one knew what reentry was all about.
Okay.
Never had it happen. In '56, I started work on that 164 HT burner.
Okay.
What we did was we took our Humades 2 rocket, laid it on its side, put test specimens behind it,
Mm-hmm.
simulated the reentry.
Okay.
By 1957, we had the first object put on a Jupiter C nose cone,
Mm-hmm.
fired it into space,
Mm-hmm.
and then fired it back in.
Okay.
That proved that you could survive reentry. At that time, we had a little nose cone about that big,
Mm-hmm.
and in '57, I think it was. Yeah, August of '57 was the first true reentry.
Okay.
And on November of '57, President Eisenhower had it on TV. Showed it to the entire world.
Okay.
That particular nose cone now sits in the Smithsonian Institute.
Right.
It's got my name in along with all the other guys that worked in the lab.
Okay. Now, that nose cone was it made almost entirely of the materials that you developed?
Yeah.
Okay.
It was what we call the Micarta 259-2,
Okay.
which is a composite material that Westinghouse provided the raw materials for,
Okay.
and then we built it.
Got it.
When I say we, the laboratory
Right.
put it together.
Right.
That is the same material that Eisenhower had on TV, and it's the same material that's in that color photograph.
Right.
Because that was the test that we did to prove that it would work.
Right.
Okay, so after that, in '57, we started work on what was called the Jupiter series. The Jupiter was big enough that we could put monkeys in it.
Okay.
And in late '58, well, in May of '58, I was on my final leave in Chicago, and I got a telegram in here that says, report back immediately. They were going to test the Jupiter.
Okay. And they just kind of surprised you with this? Surprise, you're testing the Jupiter.
They didn't surprise us.
Oh,
I knew it was coming.
Okay.
I didn't know when the date was going to be that
I
they'd
see.
actually fire it,
Okay.
but I had to go back to the facility
Right.
so that when all the generals came in, I could explain what ablation was all about.
Okay.
My boss got to go down and pick the thing up. He, in turn, then measured it
Mm-hmm.
so that we knew how much ablation occurred,
Mm-hmm.
and also that it was safe, that, you know, everything had worked the way we wanted it to.
Right.
So I plotted everything out for the generals,
Mm-hmm.
and then we had this full-scale drawing. The thing was about 9 feet high. It had a base diameter of about 6 feet. Then we proved that it would work. And the next thing we did was, I didn't do it, but they put monkeys into them.
Mm-hmm.
And the monkey shots, there were a series of 3, Abel, Baker, and we lost one. And that was a different material we told them not to use, but we were ordered to use it anyway. So that was completed, and NASA decided to take over the Army Ballistic Missile Agency. In the meantime, I had gone from a Army Specialist First Class to a civilian.
Right.
Same desk, same. In the morning I was military, in the afternoon I was civilian. I still was in charge of the 164 HD burner and all of the materials that went into it. The NASA was created, and they were going to make Redstone Arsenal, where I was, George C. Marshall Space Flight Center.
Okay.
I was down there for the dedication when Eisenhower came in, and we met all of them. We all met them, and they decided, okay, we no longer were going to do material research on heat shields reentry. We were now going to do research and development of methods of testing materials at liquid helium temperatures, which is absolute zero.
Oh, so it's kind of the opposite. Instead of extreme heat, it's extreme
yeah.
cold.
So, in conjunction with the Bureau of Standards, my team, which I'm just a member of the team, developed a cryogenic facility for measuring thermal conductivity and other things at liquid helium temperatures, which is virtually absolute zero.
Right.
That finished, and the Gemini program was going, or the first space was going on outside of at the Huntsville. We had nothing to do with the first one. So they decided that they were going to continue the testing, but my job now was going to be the test operator.
Okay.
At that time, they were looking at the Mercury had already flown. The Geminis were flying, and they were getting ready for Apollo. And I got a telephone call. A fellow that worked for Martin Marietta said that they were going to get the Apollo contract. They needed a development engineer, but they wanted me to do quality work.
Mm-hmm.
I got a telephone call that I could develop the X-ray or ultrasonic testing of heat shields. And they were going to have Apollo, and I'd have the Apollo program.
Mm-hmm.
So I went from Huntsville, Alabama to Baltimore, Maryland in 1959. I was immediately assigned to a thing called SAMOS. That's a spy in the sky.
Okay.
That's where we had a heat shield up in the air, up in orbit, taking pictures. They'd shoot it back towards the Earth. It would re-enter, and we'd catch it behind an airplane in a great big net.
Huh.
Cool.
Yeah.
It was a lot of fun. But at that time, I developed the non-destructive testing using radioactive materials. Iridium-192 was one of them. And we worked on the ultrasonic measurement of materials. Developed the speed of sound in materials testing.
Mm-hmm.
The Apollo was about to be assigned, and I'd been there a little over a year, almost 2 years. And the North American Rockwell won it, not Martin Company.
Okay.
So I got a telephone call. A fellow that I'd worked with in Huntsville and also in Martin called me up and said, "John, AFCO has been subcontracted to the North American Rockwell,
Mm-hmm.
and they're going to do the development of the heat shield for the Apollo. We need a development engineer." About 2 weeks later, I was at AFCO in Wilmington, Mass.
Mm-hmm.
The day the interview, I went in, I was supposed to see the head of quality and reliability, but the head of materials engineering had his top aide meet me in the personnel office when I came in, and immediately took me down to the lab, showed me all of the good things they were doing down in the lab,
Mm-hmm.
and how we were going to develop the heat shield for the Apollo. And during the course of the day, I was shown everything they had and taken out to lunch, then finally taken out to dinner at night and taken directly to an airplane. When I got back to Baltimore, there was already an offer in there to be a senior materials engineer
Mm-hmm.
at AFCO. Unbeknownst to me, the people that originally had called me to come in never saw me. I arrived 2 weeks later, walking down the halls. Merwin Anderson, who was the head of quality and reliability, comes over and he says, "Aren't you John Johnson?" I said, "Yes, I am." He said, "Why didn't you come and see me?" And I said, "Why?" He says, "You were supposed to interview with me
Mm-hmm.
3 weeks ago."
Mm-hmm.
I said, "I didn't know that." So I went into materials engineering instead of into quality and reliability. They wanted me to do the ultrasonic testing and all that kind of stuff.
Mm-hmm.
But I went into development. That's when we get into why did we get Apollo, that big heavy one that you had.
Which one's the?
Yeah, that long
Oh,
brown one.
the big piece. Let me see. Okay. There you go.
Yeah, this is the first material that we developed.
Okay.
And when you feel it, you can feel
Oh,
how
yeah.
heavy it is.
Yeah. No, it's probably.
Okay.
Yeah.
It was
Several
obvious
pounds.
that you could not use that as the final material.
Oh, because it's too heavy to go up.
It's much too heavy.
Yeah, you make a heat shield out of this, and it's gonna be hundreds, thousands of pounds.
Right.
Got it.
So The material itself works well, but now how do you lighten it up? That's where this comes in.
Okay. Now this is a what's this material made out of?
Oh, it's 259 dash, what does it say on it?
Oh, it's it says D5-1307 something.
No, I'll find it.
Okay.
There you go. Okay. This is 259 dash, I think it's 39
Okay.
D, meaning dense.
Okay. And
So,
it's,
we had,
what do you use to make something like this?
huh?
What do you use to make this? Is
You
it
just mold it,
is
put it in a
it
big press and,
is it a plastic or is it a petroleum?
okay. That is made up of phenolic microbloons, quartz, silica, anhydrides, I think there's epoxy resin, Novolac resin,
Okay.
and phenolic resin.
Okay.
Okay.
Got it.
Now, all of these things tend to ablate very, very well.
And ablate means to.
Ablate means you heat the surface,
Mhm.
it melts the surface,
Okay.
it vaporizes the surface.
Okay.
As you do each of these things, you absorb the heat that is created
Okay.
from the rubbing.
Okay. So
the
the
air.
process. So the process of melting and evaporating
Disperses the heat.
disperses the heat. Got it.
Yeah.
Okay.
So we had an idea. What if we took that material
Mhm.
and lightened it up by adding more phenolic microballoons, which are little tiny spheres.
Okay.
They're hollow.
Okay.
So instead of using the phenolic resin,
Mm-hmm.
we now use the phenolic microballoon. But how do you hold it down? Well, first of all, this is the substructure of the vehicle. That's
So-
the face of it.
Got it.
Okay. It's got
Right.
both sides.
Right.
This is the strength of the command module.
So what you're saying is that
This takes the place of that.
so you add the microballoons, the phenolic microballoons, to this, but the problem with that is it doesn't hold its structure.
That's
Is
right.
that right? Okay. And so what you have here is.
This is the substructure for the vehicle. You build the vehicle with this.
Mm-hmm.
Now you're going to protect it.
Mm-hmm.
So if you put this honeycomb around the outside of it,
Mm-hmm.
then you, what's called gun, literally, you take and, you know how you caulk around the house?
Yep. Like a caulk gun.
A caulking gun.
Yeah.
And air controlled. You fill each one of these cells with the material.
Okay.
This lowers the density down to, I don't remember the exact numbers of the density now, but it is much lighter.
Right.
Now, how do you get around the corners?
Right.
This does not bend very well,
Right.
okay? That's what this is all about.
And this is.
That is a preformed honeycomb.
preformed how? Is it just.
When they actually glue it together,
Mm-hmm.
they mold it this way. So that's how you get around all the corners in the thing, in the vehicle.
Okay.
Okay, each one of these holes is filled. If you go the entire vehicle, there are over 400,000 of these holes. The base, the bottom of the vehicle, the aft structure as it's called, has 270,000 in it alone.
Okay.
And then the remainder of it makes up over 400,000.
Okay.
Okay, we get that. Now, how do you qualify it? Well, the box.
Uh, this one?
Yeah.
Okay. Let me
One way,
hold this or
yeah. One way is to do a test very similar to what the 164 HD burner did. And that was make a specimen that looks like that.
Okay.
There's the heat shield. This around the outside is your edge member, because this does not, it's not structural on the side. So you put this green stuff around it,
Okay.
called an edge member, to contain it.
Okay.
You take that,
Yeah.
and you mount it like this. You got a sting that holds it
Okay.
like that, and you hit it with a flame,
Okay.
just like the 164 HD burner, except this is now called the, I think it was the 5 HT, but I'm not 30.
Okay.
Sure. This simulated a joint,
Oh, I see. Okay.
the joint here, and a crack.
Oh, I got you.
Okay, you have a defect here
Right.
intentionally.
So it's designed with a defect in order to test for.
This is the testing a defect.
Okay.
That's what that one was all about. And
Let me know if you want me to grab anything.
Hmm?
Let me know if you want me
Yeah.
to grab any of those.
this one, in order to hold the vehicle in place,
Mm-hmm.
you could not press on here. You needed something more stringent,
Okay.
which is this material. That's called the shear pad.
It almost looks like a piece of wood.
Yeah, take it out of the box. So we developed a higher density material as a shear pad.
So it doesn't feel like wood, but it looks like it.
It's not.
I know. I figured it wasn't.
So that was,
So there's a bunch of pieces on it. Okay.
that was used as the attachment points
Okay.
to the vehicle.
I see.
Now you had another problem. When we did all of the NDT and X-ray testing, if every one of these things had to be full,
Mm-hmm.
and we found that a cell was not full,
Mm-hmm.
we had to develop a solid form, which was this,
Mm-hmm.
all heat cured and that,
Mm-hmm.
and then you drill or machine it out, like the plug, out
Right.
of this material,
Got it.
to put in wherever you had bad material.
Got it. Okay.
Okay. In order to test how good this stuff is,
Mm-hmm.
you made a panel,
Mm-hmm.
and then this is called a tensile bar.
Okay.
This is pulled like this
I
to
see.
determine the tensile strength.
Mm-hmm.
You also had compression specimens, you had thermal conductivity specimens, you had shear specimens, and all this kind of stuff that we did on every single vehicle.
To
that was
determine the
going.
varieties of stress that it might undergo.
Yeah.
And how strong it would be.
So then along came the 202. And this, by the way, is bonded to the top of this,
Okay.
as can be seen in here.
Yeah.
Okay, so the 202 came along, was the first time that they simulated a reentry of the Apollo vehicle. And that occurred on when was it? August 25th, 1966.
Okay.
And I was one of the contractors for the Apollo that were invited to witness the actual launch of the 202, and then we got to see the recovery on film later because we couldn't be in two places at the same time.
Right. Right.
So I watched the launch of it. Very impressive. That was a daytime launch. It went down. I forget how far, but it came. They recovered it, brought it back, and we did tests like this to determine just what the char looked like and
Right.
how everything had worked. That was fine. Then we started launching the Apollos for real. Once Apollo 1, we had 3 astronauts die on the pad.
Right.
And the reason for that was they had pure oxygen inside. Our heat shield worked too good. They couldn't get out.
Mm-hmm.
And 3 of them died. Chisholm, White, and Chaffee. I had met all 3 of them. We did a major redesign, or they did a redesign to make sure that they now were breathing air instead of pure oxygen.
Yeah.
Along came Apollo 9. Well, there's several others, one in between. But Apollo 9 in particular, which I showed you the pictures of, was a very successful launch, orbit, re-entry. And after it got back, this is the test pieces that we got
Right.
at the lab. And once they had done all of the tests on how good it was, they made a bunch of these samples which were given out to select people.
Okay.
Then they actually went to the moon, as you well know.
Mm-hmm.
We had Apollo 13 was a disaster in that the oxygen tanks in the service module blew up, put holes in the heat shield. We thought
Okay.
that's where
And what made you think that they put holes in the heat shield?
it blew up because of the defect in the equipment.
Okay.
Literally,
Right.
they had a spark in the oxygen tank, and you don't do that.
Right.
So they corrected it on a later flights. But they were supposed to land on the moon, but as you probably know, they went around the moon and came back.
Mm-hmm.
Well, now everybody's worried about, are they going to be safe to come through the atmosphere?
Right.
And we spent 3 days doing similar tests to the one I showed you here with the crack. We did it with holes, we did it with all different kinds of things. And we said that they could have a hole that was at least 5 inches in diameter
Whoa.
right through the heat shield,
Mm-hmm.
and they would have survived.
Wow.
The reason being the inside would have heated up,
Mm-hmm.
you know,
Mm-hmm.
but it would not go above 112 degrees
Okay.
inside the command module.
Okay.
When it got back, we found that there was really no significant damage to the heat shield.
Okay.
None. You know, when it blew up, yeah, their pieces
Mm-hmm.
ended up in the heat shield, but no significant damage.
Okay.
Then came time for the last launch to the moon. And the Smithsonian Institute gave me a call, well, they gave AFCO a call and asked for someone to represent AFCO at the launch of Apollo 17, the last shot to the moon. And that person had to tell the Apollo story.
Mm-hmm.
So I was the keynote speaker for the Smithsonian Institute at the launch of Apollo 17. And I got to meet the astronauts before they took off and what have you. So that was the end of the Apollo contract as far as AFCO was concerned.
Mm-hmm.
We continued to support, we didn't make any more after that, but we continued to support NASA, and we'd go out and give presentations on, this is how we built the thing, and this is how we developed it, and what have you.
Mm-hmm.
But at that time, they were looking at the space shuttle. And when they developed the space shuttle, they made all the leading edges, meaning the wings, out of AFCO material.
Okay.
So this is a piece of the very first shuttle. When they came back, they cut out samples. We did all of our tests the same way as they did the Apollo.
Mm-hmm.
And those of us that were involved in it each of us got one of those things.
Wow.
So that's the story of Apollo, but that's not the story of development.
Right. Do you want to do that tomorrow?
Huh?
Do you want to talk more about it tomorrow, or do you
Well,
want to keep going tonight? Today?
That ended.
Okay.
So now they said, what are we going to do now?
Okay.
And you know fabric, okay?
I know of fabric.
Fabric has threads going in two directions.
Yep.
Okay. They were looking at how can we actually have a material that has fibers going in all three directions.
Okay.
That's when I went to work on the 3D fabrication, meaning we wove, and that's what you saw in that other picture.
Right. Okay.
Fibers going this way, fibers going this way, and fibers going that way.
Okay.
We then take that and put a resin into it. We started out with silica fibers, then the quartz fibers. Again, this is looking forward to heat shields, because you always had a delamination problem. If you pasted these things together, when they heated, they'd come off in layers.
Okay.
Each layer of fabric would come off.
Okay.
So we came up with the three-dimensional loom.
Mm-hmm.
We did a whole lot of testing. Again, this is all the properties, thermal, mechanical, electrical properties, things like that. We ended up with a nose cone, the tip of which was made out of this 3D material, which enhanced the ablation immensely, because you no longer had any delamination.
Okay.
It was all pure ablation.
Okay.
Then we said, well, this is good till what would happen if we could make the thing out of graphite?
Okay. You mean
The
the threads?
much-
Or
Huh?
the threads out of graphite?
Yeah, well, it's the threads and the whole thing out of graphite.
Okay.
So I worked on the development of the graphite fiber,
Mm-hmm.
which later they made tennis rackets, and they made all this kind of stuff out of. We didn't see any of that. All we did was develop how to make the fiber,
Mm-hmm.
and then turned around and made 3D blocks out of the fiber.
Okay.
We'd put coal tar pitch into it and then burn it out, and put more in and burn it out, and leaving the carbon behind, and then turning it into graphite
Mm-hmm.
with high temperature. That is today used in airplane brakes.
Okay.
It's one of the primary reasons for that is airplane brakes, and it's also made into the nose tips.
Okay.
And those are used in ballistic and intercontinental missiles.
Okay.
That turned out to be lots of fun. Had many challenges. Worked on the development of the circular pieces.
Mm-hmm.
That was a lot of fun. We actually could weave a cone, which, that's fun. we finished that, and in the entire time that I worked on this, I was responsible for writing the military specifications for all of these things.
Mm-hmm.
So I had a lot of them that I had written over the years.
Mm-hmm.
And when it came time for me to retire, they called me back after 3 months and said, we don't have any spec writers. We need somebody to write the specs for these new things that we're building.
Mm-hmm.
So I went in, and 3 different times I went back and wrote the specifications for them
Mm-hmm.
before I ended my career.
Mm-hmm.
Materials that I helped develop was the probes to well, Saturn, probes to Mars, of course the lunar probes, the initial
The lunar probes, the landing modules, or or actual unmanned probes.
they were to go into the atmosphere of these various
Okay.
things and take all kinds of
Did we
instruments.
Did we know what kind of atmospheres we were looking at when we sent those probes? So we didn't know how thick it was, density, temperature.
No,
Okay.
that's why we built the probes.
Right.
And then we'd send them up, and then when they got back, then we'd learn something.
Okay.
Or when they never came back,
Right.
but the
it's-
data
yeah.
came back.
Yeah.
Yeah.
What were you expecting when I mean, you had to be expecting something when you built the materials for it, right?
Well, what we do is we come up with different, mostly in the plastics terminology, because it's lightweight.
Right. Okay.
You know, very few. We did do some metallic research. Oh, by the way, when I was doing a lot of this development work, we were requested to come up with a material that could be used on ships
Yeah.
to retard burning.
Okay.
If they had well, also for oil wells, if they have a fire, they had to come up with some new materials, which we worked on, that literally protected the steel for like 12 hours or 14 hours or something like that. Because it didn't ablate, it burned very, very slowly.
Right.
Okay. I worked on that. And then we had a request. There was a lot of problems with the leading edges of airplanes on the wings, that the rain would erode the aluminum.
Okay.
So I worked on putting coatings on the wings of airplanes, rain erosion coatings. And I did a lot of testing out in Ohio at Wright-Patt Air Force Base,
Okay.
another project that I was on. And we worked on the manufacturing of different materials for other people.
Mm-hmm.
You know, sort of the sound materials, you know, to absorb sound,
Okay.
radar absorbing materials, radar reflecting materials that you want to put on buildings, so that an airplane coming along gets a very clear message that there's something in its way.
Right.
All these different materials. And the basic thing is you take and modify the chemistry of the material
Mm-hmm.
and then do the testing on it. And I was the manager of the physical and thermal test group for a number of years. All this was going on while I'm doing all these things.
Mm-hmm.
Then I retired. And I don't do any of it anymore. But I was called back 3 different times after I retired.
Wow.
So that's where we got there. From Chicago, Illinois, to Huntsville, Alabama, to Baltimore, Maryland, to Wilmington, Massachusetts.
That's great.
What else you want to know?
Well,
I don't know anything else.
I think tomorrow,